few past papers available on Moodle. I will be releasing solutions, type solutions to the class exams, and we have some video solution or videos of me discussing some of the solutions as well. Okay, so what do we make of this question? Question 4a, 20 marks to get on quadratic residues. Like most of my questions, you see they often start off with pretty basic, giving a definition or some basic properties of the thing. So you're asked for what is meant by a quadratic residue, a non-residue, not P, where P is not prime number. Now there's only 4 marks going for that, so you're not going to be writing loads for that, but you do want to write enough to, remember, always be trying to demonstrate your understanding. Convince me you know about these things. Remember, in one of these exams, you've got at least half an hour for each question. Okay, there's 5 half hours, gives you 2.5 hours, and there's an extra half an hour. So you do have plenty of time to provide complete answers, I think, to really demonstrate understanding. Then part B is asking for a proof of one of the basic results, early results we had around quadratic residues. In that was half of the non-zero congruence classes modulo P were residues and half were not residues. And then part C is to do one of these factorized split reduce calculations to work out the Legendre symbol. Well, you have to know that first. What we want to show is whether or not there are solutions to x squared congruent to 617 mod 809. And we do that by the factorized split reduce procedure on the Legendre symbol of 617 modulo 809. And you're given a hint there that both those numbers are. Okay, so let's go through it. So what I'm looking for in part A is your best version of the definition of a quadratic residue. So let P be an odd prime number. I.e. P not equal to 2. And so what do we say? We say an integer n, or really a complex class mod n, mod P is a quadratic residue if and only if. So here's where you really want to hit the nail on the head. Very clear and exact. So it says if there exists a U in Z such that, and don't get them the wrong way around. I've seen people put them the wrong way around, and n squared is U or something. No, n is the square of something. N is congruent to U squared modulo P. Last year's exam. Let's start this recording. Yes, I did. Okay. And a non-residue if there does not exist such a U. Actually, now that I think about it, part of the definition was that we required that P did not divide n, that n was not congruent to 0 modulo P. It was non-zero modulo P, and it was a square. 0 is always the square of itself, but 0 isn't kind of admitted into the multiplicative structure modulo P. Okay, now we've got no 4 marks. I mean, there's no harm to give, maybe give a small example. You could say, e.g., modulo 5, and the residues are, well, 1 is always a residue, and then 4 is a residue as well. because 4 is the square of 2, but 2 and 3 are not. 2 and 3 are non-residues. Since, now why is that? Well, 1 squared is congruent to 1, 2 squared is congruent to 4, 3 squared is 9, which is 4, and 4 squared is 16, which is 1. All of these modify. Okay. So we see 1 and 4 occurring squares of things, but not 2 and 3. So that, I think, something like that would attract all 4 marks. Trying to remember the non-zero bit, word that in better as a person sentence. But the addition of a little example to illustrate it is good. It's good to have that as part of your definition. Any comments about that? Sure. Yeah.
Is there you said really congruence class. Is there like not superscript, or like is there a set that we can sort of refer to?
Yeah, so some people, so maybe,
general.
I mean, you could criticize me in some of my stuff here for being a bit lazy with the distinction. So, yeah, so some books would indicate, n is an integer, and something like that is a congruence class. And they might even put a subscript p to denote the modulus.
So it's like a general congruence class.
Well, if you put the subscript p, you'd mean modulo p, but without the subscript, it would just indicate some kind of a congruence class, and you'd get that from the context. But then, you have all these equations, and everything has to have a square bracket around it all the time, and it can be a little bit frustrating. And they are intimately connected. We represent congruence classes via integers.
So the definition, we just sort of need to just say a congruence class.
Yeah, well,
not. Or,
I mean, you would still get full, if you didn't have that little comment in, you would still get full marks, because when we're talking here about this relationship modulo p, but that covers other elements from the congruence classes as well. But when mathematicians talk, and when we talk about this stuff, whether something is an integer or a congruence class modulo that thing, it's kind of implied, and we don't necessarily make the precise distinctions. Okay. Okay, part B. Prove that if p is an odd prime number, then exactly half of the p minus 1 non-zero congruence classes modulo p are quadratic residues. Okay. Okay, so we let p be an odd prime. The proof of this is in the book. Well, let's see if I can, kind of reconstruct it here. So what's the idea here? Well, the idea here is kind of contained in this little example that we showed, is that if you start squaring everything, of course, if you start squaring everything, you discover what the residues are, because the residues are squares. And what you also notice is you get this doubling up. So 1 squares to 1 and 4 squares to 1. 2 squares to 4 and 3 squares to 4. Now, what's a good way of explaining why that doubling up is occurring? And I mean, you're intimately familiar with the reason why it is occurring. So give me something that squares to 4. 2. Give me something else that squares to 4. Minus 2. That's the point. Yeah. Anything that 4 squares to 16, but so does minus 4. So you're familiar with that from integer arithmetic, from real number arithmetic. But the same thing is going on with modular arithmetic. Okay, 1 is the negative of 4, 2 is the negative of 3, modulo 5. Okay, so that's where the doubling up occurs. And if doubling up occurs, that means if you square everything, there's p minus 1 elements there in total. But if they're doubling up onto the squares, that means at most there can only be p minus 1 over 2 squares. Doesn't prove there are exactly p minus 1 over 2 squares, because you could have more than doubling up. You could have some quadrupling up. 4 different things could square to the same. That's one of the points we'll have to make in this proof. Okay. So let's do this. So we can present a complete set of representatives. Again, representatives. The congruence class is modulo P. The non-zero congruence classes. As these numbers here. So we can go 1, 2, 3 up as far as p minus 1 over 2, the first half of them, and then just write down the second half of them as the negatives of those. And you got -3, -2. First half, negatives of the first half. Okay. So therefore, when we look for the quadratic residues, squares of these, we find that most p minus 1 over 2 residue, quadratic residues. So you got 1 squared is congruent to minus 1 squared. Since 2 squared is congruent to minus 2 squared, all the way up as far as the square of p minus 1 over 2 is congruent to the square of minus p minus 1 over 2. Okay? All these congruences modulo. Okay, I've listed p minus 1 over 2 squares here. Okay, but why have I said at most? The reason I've said at most is because there's a possibility that 2 of the things I've written down here are the same. Yeah. You have to entertain that possibility. Okay? They look different, but we're speaking modulo P. So things can look different, but still be congruent modulo P. Yeah. So and I think there's a couple of approaches we could take here. I got a suggestion.
Trying to get the lower bound.
Trap it, yeah. So we know p minus 1 over 2 is the upper bound. So in effect, what we have to do is rule out the possibility that 2 of these could be congruent. So we could build a proof by contradiction. We could say, well, assume that 2 of these were congruent. Yeah. Assume that 2 of those were congruent, and then derive a contradiction of some kind. Or maybe is there a kind of standard part of the theory that we could call upon that would, the Lagrange theorem. So I'd say there's two approaches I'd like to put down here. Now, we would only need to present one. So the first one will be to cite Lagrange's theorem. So consider the polynomial congruence x squared congruent to n modulo p. Now, each quadratic residue n has the two solutions given above. Yeah, because up here, for each quadratic residue n, this will be one of these entries I've written down here, and there's two things that square it. Right? So we've shown two solutions to this polynomial for each quadratic residue n. But Lagrange's theorem says such congruences have at most two solutions. Some of them will have none, where you're putting in a quadratic non-residue. You won't be able to find any x's that square to that. Yeah. But when you put a quadratic residue in, you're going to find the pair of solutions that you've listed up here. But Lagrange's theorem says that there's at most two solutions. So therefore, each residue, each quadratic residue listed at star above, so just this list of indicating it's labeling that as star, listed at star, is distinct. So there are p minus 1 over 2 quadratic residues. Okay. We'll take one of these. Okay, so that would be perfectly acceptable. Lagrange's theorem came up, before we got to quadratic residues. We're not being asked specifically about proving Lagrange's theorem here, so we can certainly refer to it. As long as you clearly state and clearly show that you know what it says. It could add a little bit too. Lagrange's theorem says such have at most two solutions since it's a quadratic, since it's a polynomial of degree 2. The reason it's got two solutions is because the degree of the polynomial is 2. So it's got at most two solutions. Okay. The second option, second approach you might take is a more direct first principles approach. Which I believe might be the one that's actually printed in the notes. So this would be, suppose I squared was congruent to j squared for some I and j in this range. Okay, so I and j would be, so the I could be 2, the j could be some pair later along in your list at star. Yeah. So we're going to assume that they square to the same thing, right? Which we know they shouldn't if I is distinct from j in this range, the first half. Now you can either present it as a proof by contradiction, where you assume here that I and j are distinct, and then argue for a contradiction, and the contradiction will probably say they're the same. Or you can present it like this. Suppose you've got I squared congruent to j squared for some I and j, and then we're going to prove that I has to be equal to j. So the only way to find a duplicate on this list is to just trivially point to the same thing twice, which is the duplicate. You're just holding up the same thing twice. So if we can prove here that this assumption implies I equals j, then we'll know that we've actually got p minus 1 over 2 distinct congruence classes listed there. So this is the goal here. So this is a congruence mod P. So when I say more direct first principles, it just uses the definition of what a congruence is. Congruence says that if I squared is congruent to j squared, it means P divides the difference between them. This kind of rule of undergraduate mathematics, of all mathematics really, when you see a difference of two squares, what do you do? Should we actualize it? Yeah. Especially when you talk about number theory, anything to do with divisibility, factoring, difference of squares always factors like this. It's often how you reason about it, okay? Now what can we tell from this? We've got P dividing the product I plus j times I minus j. P divides one or the other, yeah? Remember the sum, so this will be called Euclid's lemma, I believe it was called. If P divides a product, it must divide one of the factors. Some people even use that as the definition of a prime number. A prime number is the kind of number such that it's bigger than 1, and whenever it divides a product, it also divides at least one of the factors. That's a somewhat indirect, but a kind of perfectly serviceable definition of a prime number. Okay. So this is equivalent to P divides I plus j, or P divides I minus j. This is by Euclid's lemma. You can't remember the name, just kind of give the general version of it. So P divides AB implies P divides A or P divides B. Although you've kind of written that there, so. So now we got two cases. So yeah, let's look at it. But considering each of them, what's the possibilities for I plus j as integers? Can we trap I plus j in a range? See, it's at least 2, because both I and j are both at least 1. So the sum of them has to be at least 2. The biggest they can be is p minus 1 over 2. The biggest I plus j can be is p minus 1. Okay. Now, can p ever divide such a number? Can such a number ever be a multiple of p? No, it's too small. It's not small enough to be 0. 0 is technically a multiple of p. But it's smaller than p, so there's no multiple of p. Okay.
Why was p minus 1
Because so I'm just simply, look, for the upper bound, I just simply ask how big can the sum of two numbers be? Just when each of them are their biggest possible value. P minus 1 over 2 plus p minus 1 over 2. Yeah. So, which means p does not divide. P does not divide. Not for any funny proof by contradiction reasons, just it can't, because of where I and j come from. P cannot divide I plus j. So therefore, p divides I minus j. And we can do a similar thing. Let's try and bound I and j. What's the smallest I minus j could be? 0. Choose I and j the same. It could be. Oh, now we could go positive and negative. So really what I want to talk about is the absolute value of I minus j. Okay? You could choose the I to be the bigger one or the j to be the bigger one. But really interested in just the absolute value. How big could the absolute value of the difference be? P? P minus, so you said P minus 1 over 2 minus another 1. Because you're talking about how far apart can I and j get from each other. Well, the furthest apart they can get is if one of them is the last one and one of them is the first one. So what's the distance between those two numbers? Well, the distance from that to 0 is P minus 1 over 2. So the distance from that to 1 is P minus 1 over 2 minus 1. P minus 3 over 2. Yeah. So this is, the furthest apart they can get is P minus 3 over 2. But P has to divide I minus j. So what's the only multiple of I minus j you can have? 0. Therefore, I minus j equals 0, as this is the only multiple of P. In this range. This range we're talking about is here. Yeah. So I equals j. So what were we trying to prove here? We were doing the more direct first principles approach. If we assume that 2 of the entries in my list star, which is P minus 1 over 2 long, we assume the 2 of them are the same, modulo P, we're forced to the conclusion that I really just pointed at the same one twice. So in other words, they are P minus 1 over 2 distinct things listed here. Each of them indicated as a pair of values, they come from squaring a pair of values. These are the P minus 1 over 2 quadratic residues. So have we finished the presentation? So I've said there are most P minus 1 over 2 quadratic residues. Yeah, where did I say that? So I set that up here. Most P minus 1 over 2 quadratic residues. One way was Lagrange's theorem. The other way was this one. So just to finish off 2. So that means all P minus 1 over 2 entries in the list star are distinct quadratic residues. So there are exactly P minus 1 over 2 quadratic residues. So you gotta, there's at least 2 ways of doing that proof then, to do that second step. But a very simple principle to get you started. You just when you square a positive and a negative thing, they square to the same level. Okay, that's familiar just from integer arithmetic. And the extra little thing you have to prove about is to prove that you never have more than 2 to 1. You never have 4 to 1. Sorry?
You don't have 0. 2.
Yeah, so each choice of n here either has 0 solutions or exactly 2 solutions.
Yeah, those 2 are literally the same.
No, the 2 solutions are different.
Yeah.
They're positive and negative ones, right? Yeah. But this
non-congruent.
Yeah. Yeah. Any other questions about that? Yeah, so because in that case we're dealing with P as an odd number, it's an odd prime. Well, for any odd modulus, the residue class is modulo that. The non-zero ones, there's an even number of them. So an element is always distinct from its negative. When the modulus is even, then there's an odd number of residues, non-zero residue classes. So there is one exactly in the middle, which is its own negative. So modulo 6. Yeah, so it wouldn't occur as a pair.
You're trying to compare
Yeah.
elements from like you say, left side,
You just have to worry about whether your thing splits into 2 halves or 2 halves with one isolated one. Yeah.
Just don't quite understand. I get where I equals j,
Yeah.
All that part. Just trying to work out how do they conclude that it needs to exactly be.
Yeah. So
From that equals zero.
remember where we got to first. We were able to write down a list of quadratic residues. And my list was p minus 1 over 2 entries long. So that means there's at most p minus 1 over 2.
Right, okay.
Because the worry is, this first one could have been the same as one that you meet halfway along. Yeah. But two of these could be the same. So I don't mean the pair of square roots, so to speak. I mean this first quadratic residue, which is 1, and this one in the middle. So, because if they were the same, then there'd be less than p minus 1 over 2 quadratic residues. So we have these two ways of proving it. So this way of proving it was, well, okay, suppose you do have that I and j, which are two choices from 1 to p minus 1 over 2. So the I and j would be two positions in his list. Suppose they did square to the same thing. We argue, and the conclusion we get is, no, you didn't really choose two different positions on the list, you just kind of chose the same one twice. So obviously it's congruent to itself in the square root. Yeah. But so the only way to get two things squaring to the same from when you choose them from this list of first half of non-zero residue classes is if you trivially choose the same one twice. So that means each choice of I from this range gives you a new distinct value when you square it. So there's so that means there's at least p minus 1 over 2 quadratic residues. You've already proved there's at most.
Okay.
So that is exactly. Yeah, I'd already said there's at most p minus 1 over 2 residues. Now I'm saying all of them are distinct. So that means that is exactly. Okay. Any other issues with that? Questions with that? Okay, then the last part. So that's a kind of proof standard theory part. Then the last part is a kind of example of trying out an algorithm. So are there solutions to x squared congruent to 617 modulo 809? Yeah, you could sit there for half an hour in the calculator. If you work quickly, you'd probably discover yes or no. You might encounter a solution, trying squaring everything. But no. So the question says, use the law of quadratic reciprocity and other relevant properties to show that there are no integer solutions to this combination. Now, again, think about demonstrating your understanding. I think it'd be good here to start off by listing the three key properties: the factorized, flip, reduced property. Write them out, indicate, give a quick definition of them, and then you can launch in, do the calculation with kind of minimal reference up to each of them then. Or you could kind of launch straight into the calculation and give it perhaps a more detailed reference to each property as you use it. So are there solutions to this? I.e., what is the value? What is the value of the Legendre symbol? (617) 809. Okay. So we will use quadratic reciprocity. In fact, well, I think I'm just writing them out for our benefit here and now. These things are listed on the formula that you get in the exam. The quadratic reciprocity is. Yeah, not all of them.
2 minus 1.
You get given 2 and minus 1 as well. So the quadratic reciprocity law says P and Q distinct odd primes. If P and Q distinct odd primes, then the Legendre symbol TQ plus 1, well, let's say negative, no, it's negative QP if both are congruent to 3 mod 4, and it's equal to QP otherwise. That's the law of quadratic reciprocity. Call that 1. 2. The Legendre symbol modulo of prime is a multiplicative function. I.e., if GCD of A and B is 1, if A and B are co-primed, then the Legendre symbol of ABP is the Legendre symbol AP times the Legendre symbol BP. And the third property is the congruence property, which just kind of says that, well, really the Legendre symbol is a function on the congruence classes. Well, not only on individual integers, but because it's talking about whether or not something is a quadratic residue, really it's a function on the congruence classes. So if n and m are congruent, what P, then the Legendre symbol is equal. So these are our 3 properties. I've labeled them 1, 2, and 3 there, so we can refer to them easily. So 617 and 809 are primes. It's given in the question. So here we go. Now the sequence of moves is factorize, flip, reduce, factorize, flip, reduce, factorize, flip, reduce. So where do we come into it? Which one do we do first? Flip. Yeah. You can't factorize because the 617 you're told is prime. You can't reduce it because 617 is already reduced modulo 8. So the only available move is to flip it using quadratic reciprocity. So this is equal to 809 mod 617. Now you have to stop and think, do you need the extra minus sign? You need the extra minus sign if they're both congruent to 3 mod 4. If not, you don't. So just test one of them. 809 is congruent to 1 mod 4. Yeah. So you don't need the extra. Minus. So this is by 1. So our since is covering our absence or presence of the minus sign here, since 809 is congruent to 1 mod 4. Okay, it's not the case that they're both congruent to 3. So that's a flip. Then you want to do a reduce. So that's what, 809 minus 617 is. Sorry, what is it?
192.
192. So that's by 3 as 809 congruent to 192, not 617. 192 is a composite number, so we'd like to factorize it. And it factorizes as 2 into 96, so that's 4 into 48. 8 into 24. 16. Let me take a 4 out of that. 64 into
16 times 12.
Yeah, 16, but take some more 2s out.
I just
16
said 16 2 to the 4 and then just consider it as a 1, 2 because they're not.
Yeah, so 32 times 3. No. 64 times 64 times 3. It's 2 to the 6. Right. That's a bit around the house. So 2 to the 6 times 3. Did I misspeak when I said Actually, now that I think of it, I misspoke up here. We don't need. Yeah, no, I was thinking of the Euler-Tauschen function. The Euler-Tauschen function is multiplicative in this sense that you need the GCD AB equals 1. Actually, you don't need it. It's not needed. The Legendre symbol is completely multiplicative. So it's just whenever, for any product AB, the Legendre symbol will factorize. Completely multiplicative. So I was worried here because I wanted to factorize the 6th power out as well. So this will be 2 modulo 617 to the power 6 times 3 modulo 617. So that's by 2. Now the 6 is useful because it's even. Yeah. So this Legendre symbol is either +1 or -1, but I don't care what it is now because it's only going to be raised to the 6th power. So that means this just immediately goes to this. 2, 617 equals +or -1. And it's to the power 6. Yeah, is that look good? So now we can flip again. So this is 617 modulo 3. Do we need the extra minus sign? 60 is a multiple of 4. Carrier 1, 17 is congruent to 1 mod 4. So no, so this is by 1 as 617 is congruent to 1 mod 4. Now use the congruence property. 3 into, so you're just reducing 617 modulo 3. Divide 617 by 600 is divisible by 3, and then 15 is goes to 2. 2 mod 3, so that's by 3, since 617 is congruent to 2 mod 3. Now you see 3 is tiny, so you can just say that is -1. Since 2 is not a quadratic residue, it's a quadratic non-residue, it's not a quadratic residue of modulo 3. As 1 is the only residue of mod 3. Remember, there's p minus 1 over 2 residues, so modulo 3 is 1 residue, it's 1. 2 isn't. So we get a value of -1 at the end. So the original question was posed, are there any solutions to this? So the answer is no. So there are no solutions to x squared congruent to 617 modulo 809. Since 617 is a quadratic non-residue. Hope we covered everything. We gave a good account of it there. Nicely indicated the 3 key properties. Using them in every step we have justified. Yeah. And a nice conclusion to it, which kind of answers the original question posed. Okay, any questions about that? Sorry?
Is there ever a case where you just can't value?
Is there ever a case? Well, in principle, no. As long as you can do the factorizations. That's the hardest thing to do.
So if obviously it's large.
Yeah, if it's large, I mean, but if it's within the scope that you're always able to factorize any number, then this can always happen, and it will stop because the numbers are reducing. The modulus is always reducing because of the flip, quadratic reciprocity, and then the congruent reduction. So eventually you'll hit something quite small that you can just know whether it's a residue or not. As long as you just keep track of the minus signs. That's all you're doing. Okay, good. So see you. I've got the tutorials tomorrow afternoon, so I'll see you then.
can look at some more exam papers or look at some of the quadratic residue exercises as well. Super. We're nearly finished marking it. I know everybody's anxious for it, so we're finishing it off as quick as we can. Okay, then.